Delaware Tech, Chemistry 100, Chemistry 110, Unit 3 continued, Atomic Mass. We talked about atomic number and mass number, and now we're going to talk about atomic mass. I understand these three phrases sound very, very similar, but please do not confuse them. Atomic number is a whole number. It's the number of protons. Atomic mass number is the number of protons and neutrons, another whole number. But atomic mass is not a whole number. Atomic mass is the average mass of one atom of a particular element. And the reason why this is a little different is because each element has its own collection of isotopes. And each isotope has its own isotope mass, its own isotopic mass. And the isotopes may vary in abundance. So you want to take the average of all the different atoms of each of the different isotopes, accounting for how much of each isotope there is. And that requires a little bit of calculation. Now, the units we use are the atomic mass units, but they're more recently starting to be replaced with another unit called the Dalton. The Dalton is exactly the same thing as the atomic mass unit, or AMU. It's named after John Dalton, if you remember the rules of atomic theory from John Dalton. The Dalton used to be defined by looking at carbon-12. This is the isotope of carbon that has 6 protons, as all carbons do, and 6 neutrons. And what they did was they looked at the mass of carbon-12 and they measured the mass as best they possibly could, and they divided it by 12. In other words, they assumed the protons and neutrons were the same. They are not the same. They're close, but they're not the same. They wanted something that had roughly the same number of protons and neutrons. And then they just divided it by 12, and they said, that's going to be 12 atomic mass units. And as it turns out, May of last year, May of 2019, the international body that does standards said, okay, we're not going to do that anymore. We're going to actually define the atomic mass unit based on something else. And it's a bit complicated, but it was actually for very good reasons. So now the atomic mass of carbon-12 isotope, the isotope mass of just pure carbon-12, is now 11.999999958. But don't worry about that. You're not responsible for remembering any atomic masses. You're going to calculate them from information about the various isotopes. So remember, one atomic mass unit, which is the same as one Dalton, is roughly 1/12 of the mass of a carbon-12 atom. In other words, the mass of one proton, or the mass of one neutron, is about 1 AMU. It's not exactly, and that amount being incredibly tiny, an AMU is actually about 1.66 times 10 to the minus 24 grams. So we're talking about an insanely small amount of mass, the mass of a proton or neutron. And here are the actual number of AMUs, but take a look. The mass of a proton is about 1 AMU. The mass of a neutron is about 1 AMU, and the mass of electron is about 0 AMUs compared to the other two masses. So this is why we add protons and neutrons together to get a relatively average mass of a particular isotope, but we have to figure out the mass of all the isotopes within the entire element. So we need to average all of the masses of each of the isotopes based on their relative abundance. We also call that fractional abundance or decimal abundance, but it's usually given in percent. So, before we get into actual calculating, let's do a little analogy. Let's say you have 5 rocks, and 4 of those rocks are exactly the same. They have 50 grams mass each. But one of the rocks is a little heavier. It has a mass of 60 grams. It's more massive. So what's the average mass of the rocks? Well, how do you calculate averages? You add up all the masses and you divide by how many you have. That's how an average is calculated. So we have 4 rocks that are 50 grams, so that's 200 grams from those rocks. And we have one rock that is 60 grams, well, that's 60 grams from that rock. You add it together, you get 260 grams. We have 5 rocks total, so we divide that 260 by 5, and we get an average mass of 52 grams. Does that make sense? Well, if most of our rocks are 50 grams, and only some of our rocks, in this case one of our rocks, is 60 grams, we expect our answer to be always between the two numbers. It has to be between the two numbers, 50 and 60. But since we have more of the 50, we expect it to be closer to the 50. And 52 sounds pretty good. So we probably did this math correctly. But what if you have a lot more rocks? Remember, we have a lot more atoms to deal with, so we have a lot more rocks. And let's say you have 100 rocks, not 5 rocks. And 80 of them have a mass of 50 grams. And 20 of them have a mass of 60 grams. In other words, 80% are 50 grams and 20% are 60 grams. Well, you're not going to add up 50 plus 50 plus 50, 80 times, and then 60 plus 60 20 times to do it. You're going to look at the percentages. So the way to get the average mass of the rock is you have 80 rocks that are 50 grams. You multiply those out. 20 rocks that are 60 grams, and you get a total number of grams, and you divide that by 100 rocks. Or you can say, hey, I've got 80%, which is 80 divided by 100, are 50 grams. And I have 20%, which is 20 divided by 100, or 0.20 times 60 grams. And I multiply that out. And I don't need to divide by 100 because, remember, the percentage builds in the dividing by 100. And then we multiply it out, and we get these two pieces. We add up the two pieces. Now, each of the pieces, you see, is 40 grams and 12 grams. These numbers mean nothing. They're just contributions to the total. By themselves, they don't mean anything. But when you add them together, you get the average mass of a typical rock, 52 grams. So let's look at the actual formula. So if you're doing atomic mass, you do the same thing. You take the decimal abundance. In other words, instead of using the percent, you divide it by 100. And the reason why we do that is because decimal abundance is equal to the percent abundance divided by 100. How do we know that? Well, it turns out the word percent is from two Latin words, per centum, which literally means divide by 100. So when you see a percent sign, it's telling you divide by 100. 50% is 50 divided by 100, or 1/2. It tells you what to do right there. So, to get your fractional abundance, also known as decimal abundance or relative abundance, take your percentages, divide each of them by 100, and that's your fractional abundance. And you're going to multiply each fractional abundance by its own respective isotope mass. And you have a whole bunch of pieces together. These are each of the contributions, which mean nothing, but until you add them all up, and that gives you the average mass. So here's another way of writing that using the capital sigma symbol in math. This is those of you that really love math, you might be familiar with this. Otherwise, do not worry about it. The symbol means just add all of these terms over and over again until you've used up all the different possibilities. So if we have two isotopes, we're only going to do this twice because we'll have two different isotope masses with two different abundances. If we had three isotopes, 3. Tin has 10, so they have to do that 10 times and add them all up. So it's the total that's important. So let's look at examples. Copper has two common naturally occurring isotopes. The first one, 69.1% of copper, has a mass of 62.93 atomic mass units, or Daltons. Okay, so that's your first isotope. The second isotope, the other isotope, has a mass of 64.93 AMU. And you can look at this, by the way, and this is not important to the problem, but you can look at it and say, oh, the first mass is about 63. Oh, that's probably copper 63. And the second one is about 65. That's probably copper 65. Remember, the mass number, not the atomic mass, the mass number is a whole number that's pretty close to the actual isotope mass, and you can see that it is. So remember our formula. If we want to solve for the atomic mass of copper, we have to look at our formula. The atomic mass is equal to these two pieces. The fractional abundance of the first one times its mass, plus the fractional abundance of the second one times its mass, and then we add them up. Well, if you look at the problem, we have information to get 3 of those numbers. We have the two masses, 62.93 and 64.93 AMU. The fractional abundance of the first, well, that's just based off of the percentage, 69.1%. We just divide that by 100, and that'll give us 0.691 as our F1, our fractional abundance of the first. But how do we get the fractional abundance of the second? Well, we know the first one is 69.1%, and we know that when we add up all of the isotopes, any total of anything is always 100%. So what's the abundance of the other isotope? Well, it must be 100% minus all the others. Well, there's only one other, 69.1%. And that tells us that the remaining isotope is 30.9%. So now we divide that by 100, 0.309, and now we have all four numbers. We shove them into this equation. We have one part that represents the contribution to the first isotope, and we have the second one in parentheses that represents the contribution of the second isotope. We end up with a total of about 43 AMU from the first one, about 20 AMU from the second one. The individual numbers mean nothing until you add them up and you get this total, 63.548 AMU. And I'll tell you right now, we have to round this because look at our original numbers. 69.1% only has 3 sig figs. So we have to round this down to 3 sig figs. So 63.5 will be our answer that we'll give on a test. But I'm going to tell you, this is actually remarkably close to the known atomic mass, the known average mass of a copper atom of 63.546. So we were really, really close. Here's another problem. Magnesium has 3 isotopes with the following composition. The first one, magnesium-24, 78.99% of the magnesium is that form with the mass shown here. And you'll notice magnesium-24 has a mass of about 24 AMU. We have a second isotope, magnesium-25. That's 10%, 10.00%. And it has a mass of about 25 AMU. That makes sense. The third isotope is magnesium-26. We're not given a percentage abundance, but we are given a mass, which is about 26. Now, we're not going to use the numbers 24, 25, 26. Those are just the names of the isotopes. We use the actual AMU, the actual number of Daltons, the actual isotopic mass or isotope mass. We have a missing percentage. We're going to have to figure that out. Now, you can do the formula that I just showed you on the last slide, but I highly recommend when somebody asks you what's the atomic mass of something that has multiple isotopes, make a table. And how do you design this table? Well, make a table, put the isotope on the left, and that's just keeping track of which one's which. You're not going to use it in the calculation. A column for your percent abundances, which are usually given in the problem, and you might have to figure out the last one, the missing one. And that'll be gotten by just subtracting the others from 100. The fractional abundance, you just take each of the percentage abundances and divide them by 100. The isotope mass, well, they're always given in the problem. You're not going to guess those masses. And then you're going to figure out the contribution of each one, which won't mean anything by themselves, but you'll add them up. So let's populate this table with our numbers. We know the information for magnesium-24 and 25, and we know some information for magnesium-26. We put in the 3 masses, we put in the 2% abundances, and we can immediately convert the 2% abundances to fractional abundances by dividing by 100. That was simple. We're missing an abundance. Well, we know we have 78.99% of the first one, 10.00% of the second. We add those up. That's 88.99%. We subtract it from 100, and that gives us 11.01% for the remaining isotope. We divide that by 100, and we get our fractional abundance of the third one. So now you'll see on the column that says fraction and the column that says isotope, those are all the numbers you need. Each of those are multiplied pairs. You're going to multiply each pair to get the contribution to the total. So the first one contributes about 19 AMU. The second one contributes about 2.5 AMU. The third one contributes just under 3 AMU. None of those numbers mean anything until you add them up. And you add them up and you get the average mass, what we call the weighted average, by the way, if you ever studied that in math class. The weighted average of all these masses is 24.30501 atomic mass units, or Daltons. Now, you'll look at our numbers. All of our numbers have either 4 or 6 or 7 significant digits. The lowest one is 4 when we're multiplying, so we're limited to 4 sig figs. So that would take us to an average atomic mass of 24.31 AMU. Now, what's interesting here is if you look up the actual known detailed atomic mass of magnesium, it's 24.3050 AMU. This is incredibly close to the correct answer, though we didn't have enough information to not round it so much. We had to round it because we weren't given more exact numbers for AMUs and percentages, so we're stuck with only 4 sig figs. But you see, our answer actually was good to 6 sig figs in reality. So remember, the atomic mass is not a whole number because it's an average mass of all the atoms of a particular element. We have other numbers like the atomic number and the mass number, phrases that are very similar and often confused by the student, and sometimes even by me. Those are whole numbers. So the atomic mass is not necessarily a whole number. It's a decimal number, and you can find that in every box on the periodic table, except for some of the elements near the bottom. These are man-made elements for which there's so little of them, we haven't been able to get accurate average masses of all the atoms available. But in general, you can find them in the boxes on the periodic table, and some examples would be carbon, which has an average mass, an atomic mass, of 12.0107 atomic mass units, or Daltons. You'll notice that the unit is not in the box, and there's a reason why that's true that will be discussed when we get into Unit 5. But for now, those numbers are very accurate, the best we have. Sometimes you'll see periodic tables where the numbers are rounded to only 3 or 4 significant figures, but this is the best number right here, 12.0107, known at this point. Hydrogen's atomic mass is 1.00794 atomic mass units, a little more than 1. Uranium is a much heavier element, and the average mass is uranium is 238.02891, and that's because most of uranium is uranium-238. A little bit is 234 and 235, so you expect the numbers to be close to the most abundant isotope if one of them is much more predominant than the others. So in review, the atomic number, this is what we had from the last module. Atomic number is the number of protons. It tells you what element it is, and that's a whole number. The mass number, also a whole number, is just a count of all the protons and neutrons, the heavy particles in the nucleus of the atom. The change in neutrons means a change in mass number. So when you have different isotopes of the same mass, of the same element, you're not changing the element because you're not changing the protons. You're just changing the number of neutrons. A change in number of electrons will result in a change in electric charge. So initially an atom will start with the same number of protons as protons as electrons, so it will be neutral. But then when you add electrons or take away electrons, now you end up with a charge. All of these numbers, the protons, the neutrons, the electrons, the mass number, the atomic number, and the charge are all whole numbers. In the case of charge, they can be plus or minus numbers, negative or positive numbers, as well as 0. But the atomic mass is a weighted average of the masses of all isotopes and therefore will not be a whole number. And we'll stop here and start with the current model of the atom next time.